Welcome to ERC TipsKnowLogy. In this video, we'll be talking about Introduction to 8051 Microcontroller Timer Programming. First, the 8051 microcontroller has two timers, or we also call it as counters. We call it timer 0 and the other one is timer 1. There are two functions of timers. First, it can be used as a timer, which can generate a time delay. Second, it can be used as a counter, which can count events happening outside the microcontroller. In this figure, you will see the TH0 and TL0 part of timer 0 and TH1, TL1 part of the timer 1. For timer 0, we have 16 bits from D0, D1, D2 up to D15. And for timer 1, we have also D0 up to D15. So both of them has 16 bits of data. And half of this 8 bits belongs to the low byte of the timer 0 or low byte of the timer 1, which we call as TL0. And the other one is called TL1. And the other half 8 bits belongs to the high byte of the timer 0 or the high byte of the timer 1, which we call as TH0 or TH1. Timer 0 and timer 1, as I have said, are 16 bits wide and can be used as or accessed as two separate registers, which we call as low byte and high byte. The low byte register of the timer is called TL0 or TL1, as you can see in this figure above. The high byte register of the timer is called TH0 or TH1. Now, we have TMOD or TMOD or timer mode. It sets the various timer operation modes and is used by both timer 0 and timer 1. So with the use of TMOD, we can tell what timer we will be using or which mode we will be using in our program. TMOD is an 8-bit register and 4 bits belongs to timer 0 and the other 4 bits belongs to timer 1. The lower 4 bits is for timer 0 and the upper 4 bits is for timer 1. Now in each case, the lower 2 bits are used to set the timer mode, and we have mode 0, mode 1, mode 2, and mode 3. The upper 2 bits are used to specify or to tell the operation. In this figure, you will see that the least significant bits starts from M0, M1, C or T, and the gate. This belongs to timer 0. And then the other half are M0, M1, CT, and gate. This belongs to timer 1. So the timer 1 is on the most significant bit part, and on the least significant bit, this is where timer 0 is. Example, TMOD equals 0x01 semicolon. This is a C language command to set the mode to mode 0 of timer 1 and mode 1 of timer 0. So this TMOD equals 0x01 semicolon means that we want to use the timer 1 in mode 0 or timer 0 in mode 1. Since the timer 0 is the one with the value of 1, then we may say in general that we really need to or we really want to use timer 0 in mode 1. This is how it will be distributed on the gate, CT, M1, and M2 of the timer 1. And this is the timer 0, gate, CT, M1, and M2. So the M1 and the M2 part of each of these timers represents the mode. Now, if you have TMOD equals 0x20, this means that, by the way, this is in hexa, so the TMOD in binary will be 0010, that represents the number 2 here, and 0000 represents the 0. So the first two numbers belongs to the gate, which will be 0, to the CT, which also be 0. On timer 0, we have also double 0, so the gate will be 0, and the CT will also be 0. Now, the number 10 here on the blue-colored bits represents the mode bits, which is M1, M0. And if it is 10, then this means that this is 10 in binary. In hexadecimal, we will say that it's number 2. So this is actually saying we want to use timer 1, mode 2, and we can also use timer 0, mode 0. But in general, because the timer 1 has the number 10, then we can say that the priority to use is timer 1, mode 2. Although we can also use timer 0, mode 0. Let's try another example. What if the TMOD is equal to 0x12? So this means the number 1 means mode 1 and the number 2 means mode 2. Whatever happens, the first number belongs to timer 1 and the second number belongs to timer 0. Therefore, this is timer 1 and this is timer 0. But the timer 1 will be in mode 1 and the timer 0 will be in mode 2. So it means that we can use timer 1 mode 1 or we can use timer 0 mode 2 to generate our delay. Now let's look at this in more details. The TMOD register is composed of gate, C or T, M1, M0. And again, this is for timer 1. We also have another gate, another C or T, and M1 and M0 bits. This belongs to timer 0. So on the right side, where we have the least significant bit, and on the left side, we have the most significant bit. This is the timer 1, and on the right, this is the timer 0. Now, speaking of mode, remember that the M1 and M0 represents the binary numbers for our mode. So if the binary numbers on M1 and M0 is equal to 00, then we are using mode 0. If it is M1 is 0 and M0 is 1, we are using mode 1. And 10, we are using mode 2. And 11, it means we want to use mode 3. But for this example of discussion about introduction, we will be talking about the mode 1 only. By the way, the gate or the gating control, when you set it, the timer or counter is enabled only when the interrupt pin is high and the TLx control pin is set. So it means that the gate must be equal to 0 cleared so that the timer will be enabled, but the TLx control bit must be set. Now, so just to summarize, when the gate equals 0, the TR0 or the TR1 must be equal to 1. And then the timer will be enabled. But when you make the gate equal to 1, not only the TR0 equals 1 or TR1 equals 1 to make the timer enabled. Enabled means the timer will be possible to be used. And the INT0 equals 1 or INT1 must also be equal to 1. Now, in the case of the C or T, if this is equal to 0, it means that we want to use timer, or the operation of the timer will be really as a timer. Remember that the timer can be used also as a counter. But during this discussion, we will be just focusing ourselves with using the timer as a timer generator or as a delay generator. So, the C or T must be equal to 0 so that we will be using the timer as a timer and not as a counter. Now, when you make the C or T equal to 1, then it's not used as a timer anymore, but instead, it will be used as a counter. Now, the mode 0 is actually 13 bits, and then mode 1 is 16-bit timer mode. So, in questions, for example, we are required to make a program. The mode must be stated in the question, or we should choose a particular mode between 0, 1, 2, or 3 to know which mode we will be using for our program. But for today, or for this discussion, I will be focusing on mode 1, which is a 16-bit timer mode. Now, the other mode is mode 2, which is actually 8-bit auto reload, and the mode 3, which is split timer mode. Now, moving on, again, when we have gate equals to 1, this means that the hardware will be the way to use for starting or stopping the timer. We can run the timer or start the timer by using a hardware, but we need to put gate equal to 1. Now, when the gate equals 0, it means that we do not need external hardware to start and stop the timers. Instead, in our program, we can simply write the code in order to start or to stop the timer. And that's what we will do in the example later on. Now, C or T equals 0 means the timer will be used as a timer or time delay generator. But when the C or T equals 1, it means that the timer will be used as a counter or event counter. So we will be using C or T equals to 0 because we want to use it as a timer. Now the last bits, the third and fourth, are known again as M1 and M0 respectively, and these are used to select the timer mode. Again, the timer modes are mode 0, mode 1, mode 2, or mode 3. So in this example, the 00 means mode 0 and the 01 here means mode 1. Now, aside from that, we will be using some bits of the timer control or the TCON or TCON register, which is an 8-bit register. And in this register, we will be using TF or the timer flags of timer 0 or timer 1. So for timer 1, we have the timer flag TF1. And for timer 0, we have the timer flag TF0. Also, we will be needing TR0 or TR1. This is to run or start the timer 0 or the timer 1. We can set the TR equals 1 to make it run or to make it start, and we can set them to 0 to make them stop. So again, let's focus ourselves on mode 1. Mode 1 is a 16-bit timer. This is for the meantime. We will just discuss mode 1 so that it will be easier to understand the next topics later on. An initial value must be assigned to the mode 1, which is only possible between 0 to FFFF in hexadecimal number. And these numbers will be loaded into TL or the low byte of the timer and TH or the high byte of the timer. After we load the initial values for our TH and TL, then the timer must be started. It will start to count up until it reaches the limit of FFFFH. The starting number is not supposed to be 0000 always, but we can set it to a particular number so that it will be counting up from that number. Not always 0000. That's why we need to do some calculation. What will be the initial value or the first values of TH and TL? Now, when it reaches counting from FFFF, it rolls over to 000H. In other words, there's no more number after FFFF. So the next number to follow will be going back to 000 in hexa. And when this happens, this is what we call as rolls over. And automatically, the flag of the timer, which is called timer flag or TF, will become equal to 1 or equal to high. And this timer can be monitored with our program. When this timer flag is raised or becomes equal to 1, one option would be, of course, to stop the timer. So the timer flag is TF0 for timer 0, and timer 1, we call it as TF1. After the timer reaches the limit and rolls over, in order to repeat the process, then we have to make the registers TH and TL reloaded with the initial value that we put on them in the beginning. And TF must be returned or reset to 0, while the timer must be stopped. So we will be making it TR0 equals to 0, or if we are using timer 1, TR1 is equal to 0. So this is a figure to represent what's happening with our timer. So the crystal oscillator has 11.0592 megahertz here as its frequency, and the CT will be equal to 0. This means that our timer will really be used as a timer. And of course, we will start the timer by making TR equals to 1, and then it will start counting from an initial value of TH or TL, whatever that value is, and it will count up to FFFF. When it reaches FFFF, it will be going back to 0, and that's what we call as rollover, and the timer flag will become 1. While the timer is not yet done in doing its job of generating the delay, then the timer flag the TF or the timer flag will still be equal to 0. It will only become 1 automatically when it rolls over from FFFF to 0. So the TF becomes 1 when FFFF rolls over to 0. Now, what are the characteristics and operations of mode 1? First, it is a 16-bit timer, and it allows the initial value between 0000 hexa to FFFF hexa. That will be loaded into our low byte TL, which can be TL0 or TL1, and TH, which can be TH0 or TH1. The timer must be started, and in C language, to do this, we just write TR0 equals 1 semicolon. That is if we are using timer 0. But if you're using timer 1, to start the timer 1, we will write TR1 equals 1 semicolon. Now, there's another language, which is the assembly language. And to do the starting of the timer, we can write set B space TR0. Or we can also write set B space TR1 if we are using timer 1. Third, the timer starts to count up until FFFF in hexa as we have written here. But we can also come up with binary, but it will be very long because the binary equivalent will be 4 zeros with every F or 4 ones with every F. So what will happen is it will count up until 1111, 1111, 1111, 1111. And that's too difficult to say or to write. So we'll just talk about this in hexadecimal number. That's why we prefer to write FFFF. Although in reality, these are not really the data being placed in our microcontroller. But instead, it's just really a series of ones or zeros. So again, the timer reached the FFFF. It will roll over from FFFF hexa to 0000 hexa. And it will set the high, or it will make the timer flag equal to 1 automatically. So the TF0 for timer 0 and the TF1 is for timer 1. The timer flag can be monitored, or we can look at it or check on it using our program. When the timer flag is equal to 1 or raised, one option would be to stop the timer with the instruction in C language TR0 equals 0 or TR1 equals 0 with semicolon. In assembly, we can do this by using CLR space TR0 or CLR space TR1. This is how to stop the timer in C language and in assembly language. Number 4, after the timer reaches its limit and rolls over, in order to repeat the process, TH and TL must be reloaded with the original value, or what we call as the initial value of TH and TL, and the timer flag TF must be reloaded to 0, or we will reset the TF0 or TF1 equal to 0. This will be made clear later on when we see the sample program. Now, this is the summary how to generate a time delay using timers. First, we load the TMOD register, a value telling us what timer of the timer 0 or timer 1 we want to use, and we also need to write or to put there what mode we will be using. Will be use mode 0, mode 1, mode 2, or mode 3. The second part of the step is that it will load the registers TL and TH with initial count values. Of course, it depends on your programming, but if we will be using C language, we will prefer to write this in hexadecimal number. So we will put hexadecimal numbers to TL and to TH. Third, we will start the timer. And then number 4, we will keep monitoring the timer flag TF to see if it is raised or if it is equal already to 1, which will come automatically upon rolling over. Now, we will get out of the loop only when the TF becomes high. But while the TF is equal to 0, then it will do nothing, thereby making the delay. And number 5, we will stop the timer only after step number 4, which is when we get out of the loop when TF becomes high. So we stop the timer, and of course we have to clear the TF flag for the next round. In other words, when we roll over, the TF becomes 1. Therefore, after we stop the timer, or even before you stop the timer, we can make the flag or the timer flag equal to 0 to put it back to its value of 0, which means that the timer flag is not yet, or the timer is now will now start counting again from the beginning of the delay. And then we go back to the step 2 to load TL and TH, and we will repeat the process. Now let's see an example here where we will write an 8051C program to toggle all the bits of port P1 continuously with 56.384 milliseconds delay in between. So this means that the port P1, which has 8 bits starting from P1.0 up to P1.7, or all the 8 bits of P1 will be toggled continuously, just like in the previous examples. So if P1 contains 5 hexa, it will become AA hexa. By the way, 5 hexa means 01, 01, 01, 01. And to make it toggled, it must become 1010 1010, which is in binary. So in hexa, it will be AA. And the time delay must be equal to 56.384 milliseconds, which is very specific. So we cannot just use here a simple for loop for the delay, or we cannot just use MS delay. And that's why the timer programming, or in the generation of delay in timers, there's a little complication or a complicated step that we need to do. And you will learn it here, of course. Now, we will use timer 0 16-bit mode. And when we say 16-bit mode, it means we will be using the mode 1 as previously discussed. Mode 0 has 13 bits, or 30 is in 13 bits mode, and mode 1 is in 16-bit mode to generate the delay. So we will be using timer 0 mode 1 here. Now the crystal frequency is assumed to be equal to 11.0592 megahertz. Solution here is we will calculate the initial values for our TH0 and TL0 registers, which I have discussed before, and the formula is 2 to the power of n minus 1 minus the delay divided by 12 divided by crystal frequency. And to substitute the values, it will become 2 to the power of 16 minus 1 minus the delay that we want with 56.384 milliseconds divided by 12 divided by the crystal frequency of 11.0592 megahertz. Calculating the division of that, we will get 12 divided by 11.0592 megahertz. That will be equal to 1.085 microseconds, because this is megahertz. Actually, this is a constant, 1.085 microseconds, with this value of crystal frequency, which is 11.0592. Now, at this point, we cannot divide the milliseconds by microseconds. So we need to make them with the same unit. So the 56.384 milliseconds multiplied by 1000 will become 56,384 microseconds. Now we can divide it by 1.085, which is also in microseconds. And of course, the microseconds will be cancelled, and the answer will be 51,966.8203, which will be further subtracted from 65,535. When we do that, we will get an initial values of 13,568.1797. We can round it down or round it up, so we will have a value of 13,568 if we round it down, or 13,569 if we round it up. So either of the two will be acceptable for our calculation. And let's say I'll be using 13568. Of course, this is in decimal. We need to convert it to hexadecimal. So by using the calculator, we got the answer of 3500 hex. Now, the 13569 in decimal number system, when you change it to hexa, it will become 3501. But just for this answer, what will be the TL0 for timer 0? It will be 00. And the TH0 will be 35. So, the first two number belongs to the high byte and the 00 belongs to the low byte. Now, if you prefer to use 13569, which will become 3501 in hexadecimal when you convert it, then the 35 will still be the TH0 and the TL0 will now become 01. So, both of these are acceptable. So, this is for the, in this example, let's use TL0 as 0x00 in hexa, or TH0 equals to 0x35. So again, in the discussion before, we have been talking about what will the timer do. It will count up actually from a specific value, which is the initial values that you will assign to the low byte TL and the high byte TH. In other words, the 56.384 milliseconds that we want for our delay can be possibly done by programming the TL0 as 0x00 and TH0 as 0x35. But you cannot just do it by thinking or by estimation. We have to be specific using this formula, and we found the answer to be 13,568 or 569. We will still need to convert it to hexa so that we can write our program for TL0 or TH0. Also, it's not always 0. It depends on the question. If the question is to use timer 1, then we will call this as TL1 and TH1, not TL0. Now, if we use another mode, which is not the 16-bit mode, let's say we use 13-bit mode, which is the mode 0, then the difference is that the 2 to the power of n will become 2 to the power of 13. That is if you are using 13-bit mode in your example or calculation. Now, this will be the program for our problem. And just to explain, of course, you already know about include read 51.h, which is to include the header file. In line number 2, this is where we declare the name of the timer delay. Usually, the name of the timer delay is describing what timer you are using. For example, we want to use timer 0, so we put T0. If we are using timer 1, then we might as well write T1. Now, if we are using mode 1, we write M1. And if we are using mode 0, you write M0. Although you can also write mode 2 and mode 3. But for this example, our problem says that we will be using timer 0 and 16-bit mode. And 16-bit mode is mode 1. That's why this is T0 M1. And then we put the word delay. Again, the T0 M1 delay name is user-defined. It means that you may or may not use this name. You can even use your own name. Although if you use your name as a delay name, it will not really describe the timer you use or the mode you use. So it's better to represent the timer delay as T with the number of the timer, like T0 or T1, and M1, which can also be M0, M1, M2, or M3. And we can also put the word delay to tell that it's a delay, although we can also change it to just letter D, or even we can even cancel it. We can even write T0 M1 only. But for this example, this is how we will be writing our timer delay name. So this number 2 is declaring the timer and the mode. This will declare the timer delay function or subroutine. Subroutine means a routine or steps or series of commands inside another routine, subroutine. So here we will be using timer 0, mode 1. And as I have said, you may use other names like T0 M1D to make it shorter, or small letter T0 M1D delay, or you can just write delay. Although I don't like to use delay because it does not describe or tell what is the timer you're using and what is the mode you are using. So also the number 2 line can be cancelled if you put number 15 up to number 24 to replace the number 2. So if your function is below the main function, or the user-defined function is below the main, you have to write the declaration of that function. Now, number 4 is the main function. 5 is the start of our main function. While 1, this will be repeated forever. We will toggle P1 from 55 hexa to AA hexa, just AA hexa, just like what we have been doing before in the previous examples. But the delay name now is not only a for loop or MS delay. Instead, this time we are using the timer delay function. So line number 9 will call line number 15 and it will run the following. Number 17, it will tell what mode you are using or what timers can we use and what modes can we use. So for TMOD equals 0x01, we are trying to use timer 1 in mode 0, or you can also use timer 0 in mode 1, which is discussed before. This represents mode 0 and this represents mode 1. So this is timer 1 mode 0 and this is timer 0 mode 1. But of course, we will be using timer 0 mode 1. Now the TL0 and the TH0, as we have calculated, will become 00 and 35 to represent the 56.384 milliseconds timer delay that we want. So these numbers, 00 and 35 hexa, may change depending on what timer delay you want. And then we have TR0, which will actually run or start the timer to count from the initial value 3500 hexa up to FFFF hexa. And while this is happening, while it is counting up, then our timer flag will remain 0. And because it's still 0, it will just wait. That's the heart of the delay. So while the timer flag equals 0, we will do nothing. Therefore, it will have the delay, which is equal to 56.384 milliseconds because of this TL0 and TH0 numbers. So if we change TL0 and TH0 from 0035 or 3500, that will affect the delay time that we want to use. And then let's say it's done counting up or making the delay, it will roll over, and when that happens, the TF flag will become 1. Therefore, this will now become false, and we will be going to line number 22, which is to stop the timer from running, and line number 23, which is to set or reset the timer flag back to 0 again. So this is how the timer programming is done, and I hope you understand this discussion. Now, try this. Why don't you write an 8051C program to toggle P1.0 continuously? So the difference between this example or this challenge is that we will not use the whole P1. We will just be toggling or blinking one bit, which is the P1.0. So if you go back to the program, we need to declare here the S bit P10 equals P1 caret 0 semicolon. We have to declare the S bit port variable here, which is for one or specific bit, which is P10 or P1.0. So we need to put S bit. Also, in the example here or in the challenge, you're supposed to use 10 milliseconds delay. So when you calculate the timer delay or the delay here, this will not be 56.384. This will be 10 milliseconds. And also, the mode that is given in the challenge question here is 13-bit mode. Therefore, when you calculate, let's go back to the calculation, this must not be 16. It should be 13. And go ahead and calculate the answer here. And after you calculate, you have to convert it to hexa. And after converting to hexa, you can choose between the rounding down or rounding up of the number, and you can get the value of the low byte and the high byte, TL0 and TH0. But here, this is timer 1, therefore, we will not write TH0 or TL0. We will be writing TL1 or TH1 to generate the delay. The crystal frequency is still 11.0592. Also, if you have watched the previous videos, you can also try to write to draw the circuit, to write the algorithm, to draw the flowchart before writing your C language code. For those who don't know how to draw the circuit or write the algorithm or draw the flowchart, you can watch the previous videos that we have posted in this YouTube channel. So there you go. This is the complete sample program of using timer programming to do some delay for toggling or blinking a specific port. So again, as I have explained, let's go back. This part is line number 2. This is to declare the timer delayer function, where you will see the timer number and the mode number. And then in the timer delay function or subroutine, you will always have TMOD, TL0, TH0, although it's not always 0. It can be TL1, TH1, TR1, TF1, TR1, TF1. So if you follow this way, you will always write it in this manner. TMOD, TL, TH, TR, TF, TR, and TF. So we set the mode and the timer and the mode. We initialize our low byte and high byte registers. We run the timer, and then we monitor the timer flag while it is not yet done doing the counting up. It did not roll over yet. It means this will be true. And when it rolls over, the timer flag will become 1. And when it becomes 1, then it will go to line number 22, which is to stop the timer from counting up. And we will be setting or resetting our timer flag back to 0. And then it will go back to whoever called the function, which is line number 9. Therefore, line number 9 will produce the required delay of 56.384 milliseconds. And after 56.384 milliseconds, then it will be toggled, whatever is the value of P1, which is actually 55 hexa or 0101, 0101, it will now become AA, which is 1010, 1010. So there you go. This is our example for timer programming, and I hope that you will subscribe, like, share, and comment in our YouTube channel. And thank you for your support, and thank you for watching this video. Have a nice day.